as we go, and then we'll jump over to the paper and fill in some of that too. It won't take us long to do either one. Once we get it done with this part, okay, this is chapter 14, then we'll jump over into thermodynamics. And we'll look at the four types of processes that we have: adiabatic, isothermal, isochoric, isobaric. And we'll look at the graphs that go along with that. Okay? We'll mix up a little bit here. Mr. Cox will probably talk some, I'll talk some, and who knows, Mr. Miller might hop up here. Okay, all right, let's go ahead and get started. It's 5:15. First of all, some of the things that you guys already know from some of the reading that you've been doing recently, whether it be in your nuclear stuff or the stuff that we did on Saturday, talked about AMUs, atomic mass units. Okay? When we convert atomic mass units to kilograms, we know that the conversion is to take 1.66 times 10 to the negative 27. This is the conversion. Right? And the scale, I don't know that you would need to know this on your AP exam, but it's based on carbon 12. Right? So 1U is equal to 1.66 times 10 to the negative 27th kilograms. That's what's right here. I know it's a little hard to see. I apologize. Okay? Number 3 is the atomic mass. And you know that that's the average mass of all that particular atom or element that's found in nature. So typically, it's, 16 point something or 15 point something, 15.099 or whatever if we're talking about oxygen. So it's an average. It's not what it actually is. If we're talking about carbon 12, there might be some carbon 12s, there might be some carbon 14s, others. The average is close to 12. So that's the atomic mass. The molecular mass is the sum of the atomic mass in the atoms. And you guys know all about that from your chemistry. 1 mole. Okay, up here I've got in red. 1 mole of a substance contains as many particles, atoms or molecules, and as there are in atoms of 12 grams of the isotope C12. And it leads us to Avogadro's number, 6.022 times 10 to the 23rd. Right? So that's the number of atoms per mole. So if I had a set of golf balls, and I said, here's 1 mole of golf balls, that'd be a lot of golf balls, wouldn't it? 6.022 times 10 to the 23rd golf balls. That's a lot of golf balls. So when we look at our number of moles, the little n that we're going to see here in just a second for PV equals nRT, we're going to take the total number of molecules that we have and divide it by Avogadro's number. So if I have twice this, N will be twice that number, I guess close to 12.022 times 10 to the 23rd. We'll put that here, divide it by Avogadro's number, and you get our lowercase n there. N is the number of moles. So I put over here in blue, the little n is the number of moles contained in the sample. The big N is the number of particles in the sample. We need to know what both of those are, because when we get down here into some of our formulas, PV equals nRT uses the small n, but this one here, PV equals nKT, uses the big N. There's a difference.
Hey guys, let's look at the type sheet. The type sheet does not include PV equals nKT. You might want to add that over there. It contains a lot of stuff right at the top there.
Okay? We'll stop in just a second and go through the stuff on the sheet here as we get to it. Okay? All right. So now we've established what the lowercase n is. If we have a whole bunch of molecules and we want to know what n is, just divide it by Avogadro's number and you got it. You got the number of moles. That's what you're going to go put into PV equals nRT. That's what goes there. That leads us into the ideal gas law, which many of you had in chemistry. So it's very handy because it's fairly fresh in your mind. Not only did we talk about it at the beginning of this semester, but hopefully you looked at it last semester as well. we know that the pressure here is going to be in pascals. The units are going to be important because when we see later, when we get to thermodynamics, it's going to tell us some things about the graphs that we're analyzing. In particular, the area underneath the graph. We'll get to that in a minute. So we have pressure in pascals. Volume will be in meters cubed. Meters cubed. We have N, the number of moles. R is a constant, 8.31. And that unit is joules per mole Kelvin. Now somebody asked me earlier today, do they worry about, on the AP exam, do they worry about units? Yes and no. Let's say they've got 14 points to give away, maybe it's a 15-point performance problem. And they find 14 points that they can award things for, and they're scratching their head trying to find number 15. They say, okay, if they've got 2 of the last 3 units correct, give them a point. So, your units might correspond to a point there. Some rubrics, they won't have any units on there. But I think, and I've told my guys, it's a good idea to put them down because you want to get every point you can get, especially if you know the units. Okay? So put those down.
With respect to the ideal gas constant, if you look at the top of the type sheet, and those people are currently in AP chemistry, I know we got a few of those floating around. Chemists like to use a different value that's in liter atmosphere per mole Kelvin. Okay, so if you're working a problem where you have pressure in pascals, volume in cubic meters, use the one that's in joules. If you're working a problem that happens to be in liters and atmospheric pressure, use the other one. Okay?
Do you see where that is, gang? It's at the top of your page here. Mr. Cox gave you 2 values for R. One of them was 8.31, the other one was 0.0821. So you can use either one depending upon what they give you for P and V.
Great.
Okay? I know some of mine did that when we were taking the test as well, I remember. Okay? So that's fine to do that. All right, now we get down here to temperature, and temperature's in Kelvin. Notice up here that Mr. Cox at the top of his paper gives you the conversion for Kelvin, which most of you probably know, but take your degrees Celsius and add 273 to it. That's going to give you Kelvin, so you can fill in 273 degrees Kelvin. Actually, I think it's just Kelvin, you don't say degrees. All right? Now, when we look at this formula, you guys know that when you're taking the multiple choice portion of the test, you're not going to be able to use calculators, and on top of that, you're not going to be able to use the formula sheet either on the multiple choice, and that goes for Saturday. So make sure that you know your formulas. So on the multiple choice, because you don't have a calculator, a lot of the things that they're going to give you are law of ones type thing. If this doubles, what happens to this? If this is cut in half, what happens to this? So make sure you know your formulas and the relationships between these variables. So on here, we have the pressure and the temperature are directly related to each other. P and T. Same for P and N. So as the number of moles goes up, the pressure goes up. Here, pressure and volume are inversely proportional. And that should make sense to you. So let's look at the first one. If we have pressure and temperature, if you've got a closed container and you increase the temperature, maybe you've got a can of Coke and you put that can of Coke over a flame, what's going to happen to the pressure inside that can? It's going to go up. Okay, so if you increase the temperature, you're going to increase the pressure. They're directly related. Same thing for the number of moles. Say we have that same can of soda, and we start pumping more liquid in there. We put in more molecules. The pressure's going to go up if we don't give it away to relieve that pressure. So those are directly related. How about volume? Well, if we take that can of Coke and we pour it into a liter, now there's hardly any pressure in there at all, is there? Or let's say we pop it open. Now it's got this whole area. If you're talking about the gas that's dissolved in the liquid, you know, very little pressure. Okay? So as volume goes up, the pressure goes down. So know those relationships, and I know you guys are pretty familiar with those. We've got two guys down here that did some work with this, gave us Boyle's Law and Charles' Law, and man, they're awful lucky, because I think I could have came up with that too. Put my name on it. How about you? Okay? So Boyle's Law here, PV, the initial pressure, initial volume. So what is this assuming? Well, in these particular cases, we're assuming that from initial to final, N, R, and T are staying the same. Obviously, R is a constant, so we're keeping the number of molecules the same, and we're keeping the temperature the same. So the only thing that we're changing is pressure and volume. And if we do that, this is what you get. So off of this ideal gas law, it's not too hard to come up with Boyle's Law or Charles' Law either. Okay, so Charles' Law is going to say that we're going to keep the pressure the same, we're going to keep the number of moles the same, and R is a constant. So then they relate to each other like this. VI over TI equals VF over TF, right there. Okay, if you've got a question as I'm going, please raise your hand and we'll try to answer it. If you can't read something, I'll try to help you there too. Okay, now, down here, Boltzmann's constant. I'm sure it'll be something on your constants page. I haven't looked for it in particular, but I'm sure it's there. Boltzmann's constant is pretty easy to figure out. If you look back at our formula here, PV equals nRT, N is big N over big N sub A, being Avogadro's number. Well, all he did was he took this NA right here, okay, the big NA, and he slid it over underneath the R. So there's R, 8.31. There's Avogadro's number, 6.022 times 10 to the 23rd, and you get Boltzmann's constant out of it. Well, when you slide the NA over, you're left with the N. So it's the same formula, really. It just allows you to calculate some of these things without having to go in and find moles first. Does that make sense? Okay, so it's the same numbers involved, really. So Boltzmann did pretty good too. He got a constant named after himself by moving the NA to the right. Okay, so there we go. R over NA is Boltzmann's constant. It's 1.38 times 10 to the negative 23rd joules per Kelvin. Again, something that you would find on your constants page. Okay, any questions there? All right, let's look at the kinetic theory of gases. Not too difficult of a concept to get. I hope that you can see this graph. You don't necessarily need to copy it down. It's in your book. I just put it up here so I can have something to point to. So if you got your book along, you want to open up to that, you can, or just look up here, it's the same thing. Over here on the y-axis, it says percent of molecules per unit speed interval. Okay? So how many molecules are going at a particular velocity? And it's allowing us to relate that to molecular speed down here. So how many are going at this particular speed? In other words, you can kind of look at it as the y-axis being the number of molecules at that speed, and the x-axis as being the molecular speed, except for the fact this is a percentage on the left-hand side. All right? Now, I've got two different colors here, the blue graph and the red graph. The blue graph is at 300 Kelvin. The red line is at 1200 Kelvin, obviously much hotter. And we know that if we heat up a sample, what's going to happen to the molecules in that sample as we heat it up?
Speed up.
They're going to start moving faster, isn't it? If we let all of you loose in here and had you take off your shoes and flip the switch on the wall, which turns up the heat on the floor, we're all going to be dancing around, aren't we? Well, the molecules are doing the same thing. They're going to start moving faster. And so what we see is this increase in temperature shifts our curve over to the right. Okay? Now, look down. We're going to skip, we'll come back to some of these up at the top, but look down all the way down to the bottom of Mr. Cox's sheet. Okay, we're on the front page. You see the graph that's similar to what I have on here. And it's got 3 arrows. Okay? And we want to label what those points are. The very top arrow, if you look up here, the arrow that's right in the crest of that curve, that's going to be your most probable velocity to find most of those particles at. The highest percentage of particles are moving at this speed. So for 300 Kelvin, it says on this graph that it's about 400 meters per second. That's the most probable speed. Well, it's just what you think with the red graph when it's raised to 1200 Kelvin, that here the most probable speed is about 800 meters per second. So they're going much faster under those hotter temperatures. Okay? Now, the average of these velocities is going to be your next arrow over. So you see the next arrow just to the right of the one that's pointing to the crest, that's going to be your average number of molecules. Now, why is it shifted over there to the right? Well, look at this tail end over here. Okay? We've got a lot, or maybe not a lot, but we've got some that have great speeds, kind of tailing off down here to the end of this blue graph. You see that? Well, that's going to bump the average up, and it bumps it just to the right of this crest. The next arrow over is the root mean squared velocity, VRMS. VRMS. Okay? So that's what you want to put in for the third arrow. Now, how do you find VRMS? This would be a good question for your multiple choice. You might find something on there because they can give you some easy numbers to plug in. So let's look at that. Look right above the graph. It says 5 particles have speeds of 2 meters per second, 3 meters per second, 4 meters per second, 4 and 8. Okay? We want to find the root mean squared of that sample. So the first thing that you want to do is square them all. Do that. Write down the numbers of each one. Square them all. So we know that 2 squared is 4, 3 squared is 9. Both 4 squareds come up to 16. The 8 squared is 64. Okay? Add them all up. 4 plus 9 plus 16 plus 16 plus 64. Add them up. What is it? 16, 70, 80.